Well, we've looked at Young's experiment where we have two slits producing a diffraction sort of pattern or an interference pattern with maxima and minima. We're now extending that to what's known as the diffraction grating, which is something that consists of many, many thousands of what we call slits, or they are sometimes also known as lines. So the term lines is often used as an alternative term to mean the same as the term slits. So a diffraction grating, as it says here, consists of many narrow parallel slits. And so there's a picture of a diffraction grating. You'll get to handle some in class if you haven't already done so. And how they're made, and you don't need to note this part down, but basically they're produced by ruling, it says there, a whole pile of lines on a sheet of glass using a diamond. And typically, there could be of the order of 500 lines per millimeter. So that's a huge number of lines or slits, meaning that they are incredibly close together. So in terms of your notes, I just would like you to write the heading, the diffraction grating. Take note of this first point here that just says what a diffraction grating is, and I don't think it would do any harm just to note this point down the bottom about the typical number of slits or lines that you might get. The diffraction gratings that we've got in the school here have three different gratings on them. I think the first one might be 100 lines per millimeter. Certainly the second one is 300 lines per millimeter, and the third grating has got 600 lines per millimeter on it. Okay, so what do we see when we shine light through a diffraction grating? What we've got up in this diagram up here then is a laser beam being shone through a diffraction grating, and we're getting a series of lines being produced, those lines effectively being maxima or antinodal lines or points where we get constructive interference. On this diagram down the bottom here, this is illustrating the sort of thing that we saw with water waves. Each of these slits is effectively acting like a point source, and all the waves radiate out, and there are going to be central maxima and first order maxima, second order, etc. produced by that. There's nothing on this slide that you need to put into your notes though. All right, so how does it all work? So this is just an introductory statement that can go in your notes, that when a beam of laser light, it doesn't have to be laser light, it's just we know that that is a monochromatic coherent light source, so it's very convenient. So when a beam of laser light shines onto a diffraction grating, we observe an interference pattern on the screen. All right, and that's the sort of thing that happens. A few things to note. The incident light here is incident on the diffraction grating at an angle of 90 degrees. We say that it's incident normally or along a normal, perpendicular to the diffraction grating. And then from there, straight out in front, our central maximum being produced. Then further over, our first order maximum, further over again, our second order maximum. Now that's a diagram here that I've already given you to put into your notes following on from the previous introductory statement. Okay, so this then explains the previous diagram. The pattern consists of the central bright fringe, we call them, remember, and a series of fringes beyond that. Fairly self-explanatory note there, so I won't read it out even. This diagram should give us some idea of just what's going on here. So what we've got is we've got our parallel beams of light here, rays of light, incident on each of these slits. And then the rays radiate out in all directions, just like we saw with our water waves. And what we're choosing to do, though, is to focus in on a particular direction in which those rays are traveling out. Now, somewhere way over here, those two nearly parallel rays will coincide to produce a maximum on the screen. Now, the reality is that this slit separation here is absolutely tiny compared to the distance from here out to the screen. So we can say that these two rays here are as close as being parallel to each other as they need to be. So we treat them as being parallel, and what we can see is that comparing this ray here with the next one, there is an extra distance that this ray has to travel, and that is going to be our path difference. And we want these rays to arrive out here in phase by having the appropriate path distance involved there. All right, so looking at this diagram, which just sort of formalizes things a little bit more. All right, so in your notes, write the heading formula and this introductory statement. Consider light incident normal to the grating diffracted through an angle theta. So we're choosing one particular angle that corresponds to these light rays way out here somewhere intersecting to produce a maximum or a fringe. All right, I think we can see that if we just had two parallel rays, that's just like Young's experiment here. And we would have these two rays intersecting to produce the maximum. But by having a diffraction grating, we end up with thousands of rays. But if we consider two rays, these two here, next to each other, this ray travels a little bit extra compared to the adjacent one up here. This next ray down travels the same amount extra. The next ray down, the same amount extra, and so on. That little amount extra then is what we call the path difference. Right? It just depends on what that path difference is as to whether we get a fringe form. So I want you to put this diagram here into your notes. You could either just hand draw it or print it off. It's up to you for doing that. Now if we go to the next slide, we've got an enlarged version of the little triangle. Just the triangle I'm referring to here, just to flip back, is that triangle there, or that triangle there. The other thing I just think we should take note of actually from this diagram is that that angle in there is theta, that angle in there is theta, therefore that angle in the triangle is theta, 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 etc. And we're going to make use of that fact here. So here's our diagram. We've got rays of light coming in. These are our two slits here. This is our slit separation. Now in Young's experiment, and don't ask me why, they use the symbol A to represent slit separation. This time we use the symbol little d to represent slit separation. Our two rays that we're interested in come out here like so. This base of this triangle here is our path difference. Let's write PD for short for now. And the other thing we should note is that that's the angle theta measured from this direction out here, which is where the central maximum would occur. If that angle is theta, then that angle is theta. And so we've got now a right-angled triangle. This is a right angle in there. A right-angled triangle where the path difference is the opposite side of that angle. So we should be able to figure out that the path difference then is going to be equal to, it's a separate side, so it's going to be d sine theta. And what do we know in terms of path difference for constructive interference to occur? Sorry, I've done that wrong. My apologies. Let's just tidy that up. Up here, this is where we write d sine theta, okay? The extra distance traveled. And in general, we know that the path difference down here is meant to be n lambda for constructive, okay? So we can equate those two statements and say that n lambda equals d sine theta. And that's the formula that applies to the diffraction grating. The formula we've already got for Young's experiment is a special case of this one, and we can discuss that in class. And down the bottom here, just a little note, just defining things there. So n's the integer, central maximum, n is 0. First order maximum, n equals 1. Second order, n equals 2, etc. All right, and the other thing just to be careful of is that when we use the formula, we use d for being the distance between the two slits. But what's normally quoted for a diffraction grating is n, the number of lines, and often it's per millimeter. This does say per meter, so we need to be careful. If it says per millimeter, we need to convert to per meter. So a simple example, if n is 4 lines per meter, then the separation between the slits will be 1 divided by 4, or 0.25 meters. You do need to take note of that because that's somewhere people often slip up in doing these calculations. How does this work practically? Well, one way this thing can be set up is on a device called a spectrometer. You don't need to write anything down about this slide, but we're looking down on top of this spectrometer. We have our diffraction grating here. We shine our light into the diffraction grating. At certain angles, you'll get obviously a central maximum. At some angle, you'll see perhaps the first order maximum. And so by measuring off the scale, you can measure the angle theta at which that first order maximum occurs, from which you can calculate lambda, the wavelength of the light coming from this light source. Okay, so what effect is n going to have on the both the brightness of the fringes and the spacing? So if we increase the number of slits, more slits means that they're going to be closer together, and more slits means more light sources. And so more light sources means to say that we're going to get brighter maximum. Right? So increasing the number of slits is going to give a brighter maximum. If we increase the number of slits, then our value of D has got smaller. N lambda equals D sine theta. So if everything else stays the same, if D goes down, correspondingly sine theta goes up. So the angle theta at which the maximum is going to occur is going to be larger. All right, so we could say that theta gets larger. The other thing just to think about too with this formula, n lambda equals d sine theta, sine theta, or theta can't get above 90 degrees. And if theta can't get above 90 degrees, sine theta cannot become larger than 1. And so there is a limit to how many maxima you will see before you run out of angles. And so you can't see an infinite number of maxima on the screen. There's your screen there. There's your diffraction grating. You'll get your central maximum. You might get your n equals 1. Come further out, n equals 2. At some point, you'll get that this angle here can't go beyond 90 degrees. So there is a limitation as to how many maxima you will actually be able to see. Okay, an example which I'd like you to write into your notes and work your way through. We're talking about a cadmium lamp. I've shown you a sodium lamp in class. Cadmium, simply another metal that produces particular wavelengths of light that are characteristic of the cadmium atom, and we're just concentrating on one of those waves, which is the red one, and we're saying that we get our first order maximum at an angle theta 18.8 degrees. You're asked to calculate the wavelength of the light. Now when you do that calculation, you should get that the wavelength comes out to be 6.4 times 10 to the negative 7 meters. And having worked out that wavelength, you then should be able to substitute into the formula again, this time using n equals 2 because it's second order diffraction pattern, and work out that theta equals 39.8 degrees. And we can go over that in class if you are not sure of that. All right, so what happens to white light? We had a look at this with the double slit. Wasn't particularly effective, but when you look at white light with the diffraction grating, much more obvious as to what's happening. You always get this central bright one, white line, because all of the colors can travel the same distance to get there. There's no path difference there. But then you start to see a series of spectra, and they start to overlap with each other when you've got the white light. So here's your green lining up with the green, green lining up with the green, green lining up with the green, but these other colors all forming their maxima at different angles, and so you start to get these spectral lines being produced. And one last example, a little bit more difficult example, I'd say. I'll leave you just to work your way through that and to ask for help on that in class if you need help on it.